So let's start. Good morning, ladies and gentlemen. The first idea of Professor Lesiuk was not to make any parallel sessions. But when he realized that she has to organize meeting of Polish fracture mechanic groups, we have to make parallel session, mostly from remote participants, but also some in Polish. The first presenter is Mr. Bruno Pedrosa from Portugal. Fatigue modeling of low carbon steel bolt hole from material to structural detail. The screen or the floor, the screen is yours. I hope that you can share the presentation. Thank you.
Yes. Thank you very much. You can see my screen now, right? My presentation.
Yes, and hearing you well.
Perfect. So thank you very much. Good morning. So my name is Bruno Pedrosa, and my presentation, fatigue modeling of low carbon steel bolt hole from material to structural detail. So the typical procedure used for fatigue life assessment is to use the SESJA curves derived from experimental tests proposed in the Eurocode, which can be defined as a global approach, since they rely mainly on remote nominal stresses. On the other hand, local approaches rely on specific fatigue mechanisms and material data. There are several damage formulations considering either local stresses, strains, or energy functions. And recently, Uffman proposed a damage model that rely on the dislocation density for fatigue life predictions. So in this investigation, global and local approaches are compared for a structural steel bolt hole detail. And the first part was to assess the mechanical and metallographic properties of S235 and S355, essential to define fatigue life predictions based on local models. The Uffman damage model is a strain energy based damage model, as you see in this equation. the elastic and plastic components of the strain energy density can be obtained by integration of the elastic and plastic components of the cyclic curve of the material, expressed here by the Ramberg-Osgood equation, resulting in this formulation. The denominator is given by the dislocation strain energy and the critical dislocation density. So the original formulation can then be expressed by this new equation. But it's still hard to apply how it is now. So in order to make it easier, strain-like formulation is used. And here you can see how the fatigue strength and ductility parameters can be determined. In red are identified the variables that must be defined for the selected materials, namely the strain hardening coefficient and exponent, K and M prime, and the critical dislocation density, rho C. So considering experimental results on low cycle fatigue tests on S235 and S355, smooth specimens presented in literature, strain hardening coefficient and exponent were determined using a linear regression on the relation between the stress amplitude and the plastic strain amplitude as presented on these figures. The parameters recommended in the NV standard are also presented in these tables. Comparing both materials, it is visible that an improved performance is obtained for S355, mainly for higher values of strain amplitude. In the case of DNV, the parameters proposed, it stands as a very low performance for S235, while for S355 it is closer to experimental results. From the same experimental campaign, it is also possible to define the fatigue behavior for these materials. So in this case, by selecting a model based on the local strains as damage parameter, fatigue strength and ductility parameters can be defined by fitting the model to the experimental results. So you can see here the results in the table, the table for the parameters. Then the comparison can be established with the DNV parameters, which proposes a unique fatigue curve for all structural steels. So as it is possible to observe in these figures, DNV is a good approach for S235, but it is too conservative for S355. So for both materials, DNV predictions are very low in high cycle regime. So a similar procedure was conducted for the SWT model, which considers not only the strain amplitude, but also the maximum stress as damage parameter. So the curve that defined the fatigue behavior of S235 and S355 were defined, considering the elastic and plastic components of the strain separately in order to determine the strength and ductility parameters, and the results are in the table. Then the determination of the dislocation density was conducted using the X-ray diffraction technique. So a small sample of S235 and S355 was extracted from a plate and exposed to a monochromatic copper X-ray. And then the diffractometer measures the diffraction angles and the intensity of diffracted beams. So within the 5 peaks identified in the diffractogram, the average value of the crystallite size was determined using the Scherrer equation, assuming a Scherrer constant equal to 0.89. And finally, the estimation of the dislocation density for S235 and S355 generated by the manufacturing process of the plate was computed. So a higher value of dislocation density was obtained for S355, but the average value for both materials is within the typical values of highly deformable metals. Okay, so the fatigue behavior of S235 using the Huffman damage model can now be defined. So the minimum, average, and maximum values of dislocation density were used as critical dislocation density, and as it is visible from this figure, the best agreement is obtained for the maximum value. By computing the mean square error for each curve, we see that the optimized value for the dislocation density is very close to the maximum value. And similar conclusions can be stated for S355, since it was also verified that the maximum value of the dislocation density leads to the best agreement with fatigue life experimental data. So you can see from the tables that mean square error presented in the table that for maximum value of dislocation density, the MSE is reduced to the mean. So the mechanical material assessment was completed with fatigue crack growth tests. In this slide, I present the results for fatigue crack growth on S235 CT specimens. The tests were conducted under constant amplitude of load and 12 Hz frequency. Two stress ratio values were tested, 0.05 and 0.25, and C&M constants were defined. The mean stress effect was evident since fatigue crack growth rates were higher for higher stress ratio, and all results stand below the design curve proposed in the British standard. Similar fatigue crack growth tests were conducted for S355 CT specimens. In this case, one specimen was tested under stress ratio 0.1 and another for 0.5. Mean stress effect was even more evident for this material, as you can see in the graphic, and the parameters proposed in the British standard can be considered as a conservative approach when compared to the experimental data. So the S235 structural detail selected for this study is essentially a bolt hole with the geometry described in the figure. So fatigue tests were conducted under tensile constant amplitude of load, 5 Hz frequency, and stress ratio equal to 0.1. A total of 13 specimens were tested considering 5 stress levels. So defining a linear fatigue model from the obtained data leads to a slope very close to 7, which is very distinct from the slope proposed in the Eurocode, and which can be explained by the fact that by the higher relevance of crack initiation phase, as we will see in the local approach. So failure occur in the net cross section, as is observed in this figure, and propagation phase and final rupture are easily identified in the picture. In what concerns fatigue experimental data from S355, results were extracted from Berto et al. Specimens are very similar to those used for S235, and the comparison observed in the graphic shows that there is a similar behavior. However, for lower stress or low cycle fatigue region, the fatigue strength of S355 is higher. So considering now the local approach to fatigue, for crack initiation phase, the damage was assessed by means of a numerical model without crack and with the material behavior based on the cyclic curve from Ramberg-Osgood formulation. So a set of 5 different matches were used in order to determine local stress strain field independent of the match. With the final finite element model, local stress strain field was determined for all stress ranges and allowing to compute the local damage and consequently the number of cycles based on the 3 damage models, strain, SWT, and Huffman model. So on the right, you can see the comparison between predicted number of cycles and experimental results for both materials, showing that crack initiation phase takes a significant part of the total life of the detail. So and the curve using DNV parameters is also presented, showing a low fatigue resistance. The experimental results, we have the total life, so we have to assess also the number of cycles in crack propagation phase. So it was done by computing the stress intensity factor with a finite element model based on linear elastic material properties. So K was assessed for different crack lengths, considering 100 MPa of applied stress range, using domain integral method and 5 contours. Then the results were normalized, considering the applied stress range in order to determine the relation between the delta K and crack length for different stress range values. So the number of cycles for crack propagation phase was then computed by integration of the Paris law, considering the C and M constants obtained from the fatigue crack growth tests on the CT specimens, with the stress ratio closer to 0.1. On the right, we can see that the crack propagation phase is far from the total number of cycles in both materials, showing that propagation is not dominant. And finally, adding the number of cycles in crack initiation and crack propagation phases, we can get a good comparison with experimental data. As you can see, the agreement between predicted number of cycles and experimental results is very good for the three models used in the local approach, especially when compared to the prediction based on the Eurocode. So within the three fatigue models, the Huffman model based on dislocation density led to the best agreement with experimental data, as shows the results from the mean square error. So both standard approaches led to conservative results, especially for high cycle fatigue regime. So in conclusion, the material mechanical assessment was essential to determine the crystallite size and the dislocation density for these two materials. It was possible to determine that the maximum value of dislocation density led to the best agreement with the fatigue results, and the prediction of fatigue life was led to, based on local approaches, led to best agreement with the experimental results. So thank you for your attention.
Thank you very much for your presentation. There's time for questions. You have any?
Indeed, if this is a ball, an all for a ball, I think maybe also fracking is a possible cause of damage. Are you considering in the next future to analyze, to study the possible fracking damage due to the micro sliding on the bolt with respect of the plate?
Yes. The fretting is important in bolted connections, and this is an important topic. And it's important when, especially when we have the transmission of the load between the plates, and it's in the plans to move on that direction in the future. So I think that's a very good point, and we definitely will study. We'll study it in the future. Thank you.
Any other questions? If no, thank you very much.
Thank you.
And now the presenter will be Daniela from Germany. I have to rearrange a little bit. Please use the microphone. Hello. This one. We can start. The title of presentation is Abacus UMAT implementation for evaluating shell behavior of selectively laser-sintered polyamide 12, an experimental and numerical approach. The presentation, as you can see, has quite a lot of the authors, some from Germany, some from Poland. I hope that you will tell us about the project realized.
Okay. Thank you very much. Welcome to my presentation today. I'd like to show you our work, what we have done with the Technical University of Wrocław together. And the main focus on the presentation is one experimental and a numerical approach, what we use. And the main focus was the implementation of a material and damage model inside the user material routine in Abacus. And where's the, okay, thanks. Here you can see a small outline for the next few minutes. And I would like to start with a motivation. As I mentioned before, can you go on the next slide? Yes, no. As I mentioned before, we investigate the selective laser sintered polyamide 12. That means it was an additive manufacturing process. And this material have to be also used as a construction material. And to understand what's happened inside this material, we do a characterization. And here we have done at first, of course, experimental tests like tensor, relaxation, and cyclic test. And after this, we know the material behavior, but we also have to take into account the microstructure, because it's known that additive manufactured materials have got pores and voids inside. And with all the results, we can create a numerical model and simulate it in a finite element software. And at the end, we can do a validation and hope that there is a good agreement between experiment and numerical simulation. At the moment, this one was finished. We do also the uniaxial loading test. But now what I like to present you now was the question if the model what we are create for the uniaxial testing, is it possible to use it for a shell loading? And this was the focus on this work, what I present you today. And before we know, we have done a classification by Haupt that we investigate, we do a cyclic loading with holding times. And when the endpoints of the loading times create a new hysteresis, that means you have got a viscoplastic material behavior. And the model, what we use was the Chabosh model coupled with the Gerson-triggered Needleman model. And for this one, we get a good agreement for the tensile tests and also for cyclic tests and for relaxation tests. And now again was a question, is it possible to use this model for shell loading? At the beginning, we choose one spaceman exactly where we can use the digital image correlation for. And as I mentioned before, we produce the spaceman by selective laser sintering. And we test it on a universal testing machine and use also the DIC to measure the deformation field. And here you can see a small picture of the DIC, two interesting points where we have got inside the shear stress. And here I like to show you a small movie. You will see at the beginning we have got a poor shear, and at the end we have got like a superposition between shear and tensile. And here's at the beginning the shear loading, and later you will see when this one goes outside these edges, and we have got a superposition of shear loading and the tensile loading. And now was a question, okay, how we know now, okay, what's happened outside on the surface and how it looks inside. And here we do computer tomography analysis. And what was interesting that we have got for after the printing process, 4.35% of void volume fraction. And this is much higher than when you compared with the metals. And what was also interesting, inside this diagram, you can see the void shape. And here inside the black line is the ideal void shape of a sphere. And what was interesting when we do a cyclic test, that after the cyclic test, the blue one is the virtual one, and after the cyclic test, the average curve becomes more to a spherical shape. And that means that during the cyclic loading, the voids becomes more spherical. And now that was the reason, okay, we know now all, we know now what's happened outside, we know what's happened inside, and now we have to create the model. And as I said at the beginning, we use the Chabosh model. This takes into account the isotropic hardening and also the kinematic hardening. And all inside the red parameters we all have to determine. And this model was coupled with the Gerson-triggered Needleman model. And our approach, or the most important at this work, was the following. because the normal Gaussian triggered Needleman model does not take into account shear loading. That means when we have got a small stress triaxiality, it would not take into account. And here we use the modification of Nason and Hutchinson, where they take into account and add an additional equation inside. And this one you can see here, this is the shear factor. And inside the shear factor, there's one new parameter that calls KW. And now was the question, okay, how looks the results when we all use inside, because we have to determine all the parameters of both models. And here we have started with the optimization at first in MATLAB, and you can see the experiments, the black line, and then the normal Chabosh model without any damage model by coupling with a Gaussian triggered Needleman and by coupling with the shear model. And when we focus on the end of the experiment, then you can see when we use the shear model, we have a better agreement at the ending, of course, for the damage part. And what was also interesting, because as I said before, we have the KW factor, and here we investigate how's the influence on the KW factor. And when it's increasing, it's overestimates the results and opposite. And this was the MATLAB optimization. And after this, we implement the whole model in the HUMAT. And this was a scheme of the implementation. And we use it Fortran for this one. And this is now the simulation. On the right side, you can see the boundary condition and which element type we use. And to save some calculation time, we use a half model and simulate with this at the beginning. And here you can see the result at the end. Here's the shear region. And what was interesting, the stress triaxiality, and this is what I said at the beginning. At the start, we have got round about 0. That means we are here 0. But when we look on, for example, on tensile test, we have 0.3. But we have a small superposition that it comes, that we have not pure shear, so that later we also have got tensile loading. And the results to validate it, the results from Abacus with the digital image correlation, the results looks very good. And we like to publish these results this month in a paper. And there you have got more results, what you can see. And yes, a conclusion, we have got a good agreement between the user material routine implementation and our modified model. And with the KW factor, what we see is that it's very sensitive and that we have a good possibility to use it. What we like to do in the next steps is what I said before as a void shape. And this is very impressive, because when you have got a higher resolution of the voxel size of your computer tomograph, then the pores looks more unspherical. And this is an idea what we like to have, that we maybe modified the GTN model and add also a shape factor inside. And the second approach, what we like to have at the moment, we use only the stress strain curve as an object function for determination of the parameters. And a colleague of me who is writing at the moment his PhD, he uses a thermomechanical approach. And it means that you measure the dissipation energy during the loading. And so that we have also the temperature curve as an input for the optimization, so that we have got two curves as object function, so that we have got a better fitting for the parameter optimization. Yes, this is an acknowledgement. We also work together with the Polytechnica in Poznan, with BAM, and of course with the TU Wrocław, what I said at the beginning. And I thank you for your attention, and if you have any question, feel free.
Any questions?
Not a question, just the application of this material.
It's very, how to say, at the moment, it's not really used for, often you use it for when you have got some covers, yes. When you use for, how to say, when you use some covers where you have got a more higher loading, yes. Not really for when you not use it for toys, but when you have got some, how to say, like when you have got special parts in machine where you can say, okay, this part you can print. This is, how to say, you have a complex geometry,
Yes.
then you can take this and can say, okay, this cover is broken, but we can print this one because it's too expensive to do it with a molten injection, yes, and so then you use it.
Thank you.
Yeah, you're welcome.
Any other questions? If no, thank you very much.
Welcome. So I will moderate them. Okay. Okay. Yes. Okay, so can you hear us?
Yes, yes.
Okay, so great. Maybe I go here. Yes, our next presenter is, sorry for the pronunciation, Joao Arroyado. He would like to present us a topic fatigue performance of paddle iron retrofitting solutions, a parametric study. So it's your floor and we listen to you. You can start now.
Can you see my screen?
Yes. But at the moment we see your presenter modus.
Yes, yes. I'm trying to change it.
Yeah.
Okay. Now I think everything is fine. So
Yes, now it works.
my name is João Arroyado, and it's a pleasure to be here in the National Conference on Fracture Mechanics to present my preliminary work. I will make a brief introduction about the topic, present my case study about the CFRP reinforcement, then make a brief overview on the novel topic of additive manufacturing, and then some brief conclusions and some suggestions that myself I have to develop in my future works. So, as you know, railway transports and infrastructures are expected to receive more public investment in the further years. This is because the European Union has outlined the environmental friendliness, safety, efficiency, and smart mobility as a top priority for the next few years. We know that in the beginning of the 20th century, railway transport underwent strong development with the construction of many metallic bridges in the European scenario. And due to economic factors, there is a need to extend the operational lifespan of these bridges. So, as we know by this table, fatigue is the main cause of damage occurred in metallic bridges. The traffic volume and axle loads have been increasing significantly over the years. So it's very important to study reinforcement solutions based on suitable materials. Traditional retrofitting techniques were based on the steel plates attachment, and this consisted on, as the name says, attaching steel plates to structural details. But this is not a viable solution because these plates were bulky and increased the stress states and also induced stress concentration points. So in the beginning of the century, TFRP solutions have been widely used, also in automotive and aerospace industry, but also to repair metallic details in bridges as it has been developed in the recent years. And additive manufacturing is a novel solution and also a hot topic of research with a long path of development to be made. So on my case study, carbon fiber reinforced polymer retrofitting solutions, they show a really good high strength to weight ratio, good behavior to corrosion, and also good performance under fatigue loading. Can be applied either on metallic or concrete structures, use the strengthening method, but also to repair previous fatigue damage. The CFRP shares the average stress with the steel element, reducing the stress concentration and stress intensity factor of cracked elements. The study that I've been developed was an experimental campaign carried on the puddle iron, also known as root steel, structural details representative of the Luís I Bridge here in Porto. Some tensile static testing was performed on the puddle iron only, also on the epoxy adhesive separately to infer the monotonic behavior of these materials. And also were tested some reinforced details with CFRP. Microstructural and metallographic images will be shown and some insights, to have some insights of the metallic constituents, non-metallic inclusions, and porosity. This experimental data was key to calibrate the numeric model. So, as you know, the use of puddle iron as a construction material dates to the late 19th century. Puddling was a primitive process and had a significant waste of material, owing to the high production of slag. This has a influence on the mechanical behavior and metallographic properties of the material. Puddle iron presents a lot of heterogeneities, non-metallic inclusions, slag segregation, weight structure, and inhomogeneous grain size, as we can see here by these images representing the slag. And these properties is the main cause of scatter on the experimental results that is typical on puddle iron. This is the experimental setup for the geometry of the puddle detail, tested on a ESH testing machine. This is some images about the rupture. And here is some experimental data on the static tensile. We can see that puddle iron does not show very high ductility, but we can see that one of the samples showed a really good deformation, which is typical from the scatter on the results that I talked previously. This is the experimental setup for the epoxy adhesives that were tested on MTS machine. And the objective was to compare brittle and ductile adhesives and obtain mechanical properties. So here we can see that we have like S&P, Sika Power, and Sika Dur shown to be very brittle and high strength. And Araldite Y and AR are ductile adhesives, and they showed a really good performance on deformation. This is the setup of the reinforcement solution, and we tested some different type of adhesives, brittle and ductile ones, with the CFRP and the puddle. And we can see here on these dashed lines, this is the bare puddle. And in colors, we have the reinforced samples. So we can see that with the CFRP reinforcements, we can have a very good increase on the high strength resistance. And also, if we use the ductile adhesives, we can improve a lot the ductility capabilities of this solution. So, as I said before, this experimental data was key to calibrate the numerical model that was developed in Abacus. A linear elastic behavior of puddle iron was considered, and it was modeled with an isotropic model. This assumption was made because we are in a plane stress conditions. All materials were modeled with 8-node 3-dimensional elements. The mesh size of 1 millimeter after a mesh conversion study was reasonable to give accurate results. For simplicity, the adhesive considered was the S&P, and the contact between puddle iron adhesive and CFRP was modeled as a pure master-slave contact surfaces, with the adhesive being the slave surface and the puddle iron and CFRP the master surface. In green, we have the numerical behavior that we implemented. So comparing these two images, on the left we have the bare puddle iron without reinforcement, and on the right with reinforcement. So we can see that the stress field in longitudinal direction on the comparing both, the higher stress is now carried by the CFRP plate, as you can see on the right. The stress value in longitudinal direction reduced from 450 megapascal to 332 megapascal on the reinforced one. On the strain field, the maximum strain greatly reduced, and fatigue crack initiation life estimated at a single node of maximum stress concentration for a numerical model was done based on the Morrow equation that was calibrated from the literature from Avilio Jesus and the other authors. And the parametric study was performed to evaluate the effect of the elastic models of CFRP and the adhesive on the fatigue life. So here we can see that if we vary the Young modulus, we can increase the fatigue behavior if we use the CFRP with high modulus. But this is not true for the adhesive. If we vary the Young modulus, we don't have that much improvement on fatigue life. So reinforced puddle iron and adherent surfaces behaved well with the reinforcement solutions under static conditions. We had a good increase of strength, very significant. From the numerical modeling, we can expect better performance under cyclic regime, but we have a drawback because production of carbon reinforced polymers have significant environmental impact and carbon footprint. The material production with high energy inputs, and it's also difficult to recycle. The goals were set for Europe to be climate neutral by 2050. So there is a need to find eco and sustainable solutions. And here appears the additive manufacturing, which is a process that enables the fabrication of complex geometries compared with traditional subtractive manufacturing methods. Compared with the CFRP fabrication, AM metals have a more environmental manufacturing process, featuring lower energy consumption and lower waste production. The ASTM standards has defined the additive manufacturing as a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodologies. One of the main processes of AM is powder bed fusion and direct energy deposition. Our additive manufacturing metal parts fabrication process, selective laser melting and electronic beam melting are powder bed fusion process. Some factors influence the fatigue behavior and structural performance and should be taken in account in fatigue design, build direction, surface roughness, residual stresses, heat treatment, multi-axial stress stasis, and multi-structural defects for pores and lack of fusion particles. So these factors will influence the fatigue life. This is just a brief chart of the additive manufacturing processes. And from the literature, I took some studies just to show what is the influence of this factor. And the scan velocity and laser power are the process parameters of selective laser melting that play the most dominant roles in generating porosity. So when producing AM metals, there is a need to keep very attention to these factors. The strain life fatigue data for AM PVF 17.4 stainless steel different in build directions with and without treatment. And there is also some effect of pore size and fatigue life, all of them taken from literature. To conclude, what I present here today for you was just a preliminary work that shows that long path in retrofitting techniques must be explored. AM metal parts for topological corrections and steel retrofitting have a huge and diverse solutions to be tested. Parametric studies on AM metals changing different fabrication parameters can be done. for low cycle and high cycle fatigue regimes, and for fatigue crack propagation tests. AM sheets to reinforce old metals can be studied with different adhesives and all old constructional steels, and also some comparative studies between CFRP and AM metals parts fatigue performance can be done. I want to done this in the further years. I just presented this to you because I'm beginning my PhD. So I also would like to acknowledge the project and my PhD grants. So thanks for your attention, and now I'm open for some questions and suggestions by you. Thank you.
Yes. Thank you very much. Questions? Maybe I have one question to you. You said that you modeled in Abacus, I think you. What kind of material model do you use? Do you use only linear elastic ones?
Yes, only linear elastic ones with isotropic properties. Although this is not true for the podal iron, because we know that podal iron is very anisotropic. But for the sake of simplicity, I just consider the linear regime behavior with not introducing plasticity. And the isotropic behavior was considered because we are in plane stress conditions.
Okay, thank you.
But in the future, it's good to improve the model, include plasticity, and also isotropic behavior.
Okay, so we have also another question.
I have not fully understood. How do you use AM sheet for reinforcing the existing plates?
Okay, my idea is the same thing that I have with the CFRP sheets, CFRP plates. Maybe I can do some additive manufactured sheets with a different thickness, and use the epoxy adhesives to attach these fabricated parts to the old constructional steels.
But you are removing the structural detail to be repaired and put in the lab for the additive, or are you doing on site?
There is two possibilities. There is possible to produce the damaged elements with the same geometry, with the additive manufacturing parts, but there is also some idea that maybe I can just produce a simple plate with rectangular shape, with the same geometry as I shown with the CFRP, and attach with the epoxy adhesive. So there is no need to remove the structural detail on the bridge. There is only need to attach the AM fabricated parts.
Okay, and have you in mind any post-processing of the additive manufactured part? Because generally the fatigue strength of the additive manufactured material in the as-built condition is not so good in general. So have you in mind some post-treatment?
Yes, maybe. This is just, as I said, this is just a preliminary work. I have not begun my proper study on additive manufacture in depth, and I neither done any experimental. This is just a kind of plan that I have for my PhD. But this is also good to have this suggestion by you. And yes, I know that the AM parts don't show very great performance under fatigue, so it's important to infer the factors that can influence the fatigue behavior.
Okay, good. Thank you again. And we will come to the next presenter.
Thank you so much.
The next presenter is Michał Smolnicki from our department, and his presentation is unfortunately in Polish. So Michał, can you switch to English, leaving slides in Polish?
Yes. No. I already prepared the presentation in English.
Because I think that the topic, przygotowanie modelu uczenia maszynowego connected with artificial intelligence and machine learning, can be very interesting. There's a preparation of machine learning model based on acoustic emission to identify the causes of composite degradation, can be quite interesting as a novel So the screen is yours.
Yes, thank you very much and welcome all in Wrocław. As you can see, I'm also coming from the Wrocław University of Science and Technology. Unfortunately, I cannot be in Wrocław now due to other conference, but I will present that virtually, and I will be doing it in English for better understanding for all participants. This presentation is based on the preliminary study, which is a part of the larger project, which I done under the Pro-Quality subsidy for the development of the research potential from our faculty, and is meant to test possibilities of using machine learning to cluster data that we obtained from the acoustic emission. So I will present the main idea and also the first results that we did on the data that we obtained in the past, just to show what we can do and what have to be done in order to be better in the future. First, the idea of the material. In this research that I will present the results of, the data was obtained on the fiber metal laminates. So maybe just a few words, because it's maybe not the most common material. It's basically the layered composite, which is consists of layers of metals and also classic fiber reinforced composites. This one is actually based on the glass fiber and aluminum, and also on the polyamide resin, not resin, polyamide matrix. So it's meant more for the automotive industry than aeronautical. But anyway, for this research, it is only like material for obtaining the data. So we did some experiment. Two experiments that we used for the data was DCB and NF tests. And these tests are characterized by the fact that we use pre-cracked specimen and we load it in two modes. DCB, double cantilever beam test, is meant to reflect the mode 1, so opening of the crack, and the NF test and notch flexural test is meant to reflect the mode 2, so more of the shearing type of loading. They are realized on the classic universal testing machines with some additional equipment. On the left image, you see the equipment from the double cantilever beam test. So we have also the sensors from acoustic emission. You can see also the preamplifier. This is basically the setup that was done. But now the general idea of clusterization of acoustic emission signal. So you see this small block idea scheme, but it has to be said, why even bother with using something like machine learning to cluster the acoustic emission signal. So I will go fastly through this scheme, and then I will introduce why. So the first step, of course, is an experiment. We start from that. We have to have the data. We obtain some databases from the acoustic emission signals in form of this volume primary data and volume transient data. It's a characteristic for our system that we have of acoustic emission, but if you have other, it would be very similar. Then we need to process the data, have some resultant SQL database, and then we go through few steps like data standardization, feature selection, cluster number determination, and then in the end we have clusterization. So we split data into the groups. And now I will try to go through all these steps, explain them a little bit, and show what we can have in the end. So first, acoustic emission, what we really have from the experiment. If you are not familiar very well with acoustic emission, basically we register the waves. We register, you can say the sound, but it's really like elastic wave, and we register its properties. Or later, maybe we have some features of this wave, which is simpler to store and simpler to process. So we have basic acoustic emission features that are directly taken from the wave, as you can see on the picture. And there are also the derived acoustic emission features, which are calculated by, subtracting maybe maybe doing some division or something like that, arithmetical procedures, and we have them to process. And the thing is that if you look on the table on the right, it's not even like a half of possibilities, it's just a fraction of possibilities. So you can expect that we have a lot of features to be dealt with. And the thing is that humans are very good in processing data. If we have like 2 features, 3 features, 2-dimensional charts, 3-dimensional charts, we are good in looking into them. But when we have like 20 features or 40 features, now it's like humans are not the best in processing them. Of course, we can be smart and we can say like, okay, the most important features are like amplitude or frequency, so we will only use them. And this is basically what people usually do. They focus on these 2 or 3 the most important things, and they try to make some assumption or splitting by themselves. So if you go to the literature, you will see some characteristic that say, okay, if you are over the 400 kilohertz, then it means that it's something, etc., etc. However, we lose a lot of data, because if we use only few of them, then of course it's not the best what we can do. So now this is why we want to use the machine learning. Machine learning will let us to use all of this data, or at least choose the most important one, but not just by our opinion, but by the facts. And in result, we get the better results. Of course, dealing with the machine learning means that you need to include some characteristic steps, like standardization or normalization of the data. Because the problem is that if I go back to the previous slide, you have things like amplitude, which are in decibels, and they can have values between, let's say, 0 and 100, and then you have something like a frequency that can have value, I don't know, between maybe 0 and 1000. So obviously, if we just introduce this data as it is, we have some bias, which is not good for our results. So we need to standardize or normalize. These are normal procedures that we use in machine learning. Which one is better? This is to be checked, to be processed, and then we have some something that we can use in the future. But this is just an example of min-max standardization, which, as you can see, change the range of the data to some arbitrary range, in this case 0 and 1, but it doesn't change the distribution of the data, which is very useful because we don't lose some information. And it's used when we don't assume the data has a normal distribution, which is often not a true assumption for the acoustic emission data. So this is very useful. Feature selection is another step which is very important, because yes, we can use all of them, all of these features to find the clusterization, but it can be computationally not efficient, and also sometimes, which is maybe counterintuitive, using more information is worse than using slightly less information. This coming from the information theory, and it can be checked for more details, but this is fact. So there are different options. First one is just intuition, which is good sometimes, but not always. So probably we want to have some procedures that are science-based. And there are different approaches. Some people use the principal component analysis, and I, in my research, proposed to use something that is called Laplacian score, was proposed some years before today. And basically, it can show us which features have the biggest potential. Then we can choose arbitrary number of them and process to the next step. Then the very important question is how many group of points I want to have. And of course, there are some methods well known in the problem of clusterization, if we talk about the machine learning, because of course these tools are not new for the informatics. They are not that well known for the maybe mechanical engineers, but also they are used. I will tell you a little bit more in the next slide. So we have few methods. 3 of them I present on the slide in this very short thing. But the thing is that we calculate some numbers and then we are telling like, okay, higher value, maybe it's better, or smaller value is better, and we can compare. What is important is to understand that because we analyze the physical data, we also have some understanding of what is going on. So we know that probably for the damage in composites, we have few possible causes to this damage. So we know more or less what is the number of the cluster, but anyway, we want to check. This is exemplary results of this check. So you can see that, for example, for DCB, it's quite clear that the 3 is the best number of cluster, which is fairly okay with our scientific knowledge. Also, for the NF, it's a little bit harder, but we also can tell from that this is 5. And also it makes sense if we think about the mechanical basis. We can go into detail about this method, but maybe for now, the most important fact is that you can find the best number of clusters, you can analyze how this information was derived, and check if it's along with the mechanical knowledge. And of course, clusterization method, it's important to choose the best. So usually, most of the scientists that even bother with doing that choose the K-means algorithm, which is the simplest, which is fair, and this is the reason why it is popular. But also it has a lot of downsides and it gives not the best results. There are other approaches like hierarchical clustering, density-based clustering, or fuzzy clustering. And my idea also in this project is to check different options that are maybe a little bit harder to implement than K-means, but not that much, and check which one is the best for the problem from our class, so damage of the composites. Here is just a block schema of 3 methods that I used in my preliminary research. So I check the K-means, of course, to have some comparison, and I check one fuzzy approach, which is fuzzy C-means, very similar to K-means, but just with the fuzzy approach. So one data is not necessarily only in one cluster, but rather as a percentage probability of belonging to a given cluster, and also the spectral clustering, which has some pluses, like it is better in recognizing more convex faster, and it pay off, let's say like that. And the results, as you can see, are not that great readable because of the fact that it's very hard to show multi-dimensional data on a slide. So I choose to show just the 5-on-5 grid, which representing all pairs of features versus each other, which is not the best, but it's hard to visualize that in better way. And this is also the reason why we even bother with machine learning, because if it's hard to visualize, it's hard for human to process. And you can see some results how the clustering is done. I don't want to show all the results because it will be very boring for sure. But the summary is basically that there are differences between these methods. The K-means, of course, gives us potentially the worst results. You can use Laplacian score. I think it's very good alternative. This is my opinion on that, and I will be using that in the future. The determination of cluster number is done with classic method, and I think they are sufficient. And the thing is maybe that the important thing in a summary is also next steps. So I see very important step to be done, and we need to first have some knowledge a priori, the clustering, which I think we can obtain by doing experiments on singular mode of damage. So we have something to compare, because now we get the groups, but we don't know which group is which cause. We can suspect with our classic knowledge, but it would be better if we have something to compare a priori. So this is next step that I will do, and it will be not longer unsupervised technique. It will be mixed, like supervised with unsupervised machine learning. So this is everything that I prepare for today. Maybe there are some questions that they
Thank you very much. Do you have any questions? Well, so I have one. What kind of software you are using in such methods? The software is a crucial point to discuss. So
Yes,
your own or MATLAB, Mathematica, or Python?
yes. Okay. So basically, here are two steps. So first step is dealing with this big data, and because the data come from the acoustic emission system in form of the SQL database, I also process them using the SQL. So there are just simple scripts written in SQL language to process the database and create the resultant database on which I will process later. So this is first step. Not very complex, but you need to do that, and also the data is large, at least for us mechanical engineers. So it is, I think, good approach. And later I use the Python. Of course, you can use something else. I use Python because I also use it for dealing with Abacus. So this is natural for me. Also, this is the language that I know, let's say, better than others. So this is the choice. And also the Python has a very good capabilities with machine learning. So it has some pre-written libraries that are very useful. So later I write my own code, but I of course use some code that is available publicly to make it faster. So basically I tailor the code because the things that we are doing are specific. So this is not something that you can find, but for some parts I use external libraries. But you can get the result like that in a other stack. Here, I think this is not the most important. Just Python. I think it's easy to deal with for that. But MATLAB could be also the way, I think.
Thank you very much. Any other questions? If no, I go to rearrange the screen and
Okay, so we come to our next presenter.
Ricardo Branco, the second one. Yes.
Okay.
University of Coimbra.
Okay, so the next presenter comes from the University of Coimbra, Ricardo Branco, with the topic fatigue behavior of laser power bed fusion 18 nickel 300 steel under variable amplitude loading. So it's your floor.
Thank you. Yes. Good morning. So my name is Ricardo Branco. I come from the University of Coimbra in Portugal. I'm going to talk about the fatigue behavior of maraging steel under variable amplitude loading. It's not working. It's not working. Yes, now it's working. Thank you. So this is the outline, motivation, and a few conclusions. So maraging steel produced by additive manufacturing is currently used in different types of applications like aerospace, automotive, biomedical. But as you know, materials produced by additive manufacturing have some shortcomings. For example, they are very sensitive to surface roughness, and they have different types of microstructure heterogeneities like cavities and contaminations and melted particles. And under variable amplitude loading, there is a high risk of fatigue failure. So it's important to better understand the fatigue behavior and the failure mechanisms in order to develop durable and reliable components. So we are working together with a Portuguese company that produces large-scale molds, aerofuel. And the idea is to better understand the fatigue behavior under variable amplitude loading, because there is very limited information regarding the behavior of this material under this kind of loading. So in order to meet these goals, we designed the experimental campaign. So here you can see the tested geometry and the fabrication parameters and some properties evaluated via monotonic tensile tests. And here we are trying to explain the experimental campaign in terms of fatigue tests. So we conducted two types of tests: constant amplitude under fully reversed conditions for different strain amplitudes, varying from 1.0 to 0.35. And we have also conducted some tests under variable amplitude loading using the same strain ratio. But in this case, we defined a two-step loading history. So 3 cycles with an increasing strain amplitude varying from 0.5, 0.75, and 1. And the second step with the same levels, but in opposite inverted application cycles. So in this case, we tested 4 different maximum values varying from 1.0 and to 0.35, and we repeated the tests 3 times. So before testing the material, we evaluated the microstructure and the hardness profiles, and after the fatigue tests, we analyzed the fracture surfaces by scanning electron microscopy. So let me show you some results. Firstly, I would like to show you the microstructure in different directions, longitudinal and transversal. So firstly, we can see that the microstructure is rather coherent. We also can clearly see the laser passes in both directions. And it is typically a martensitic microstructure. We have found some martensitic needles in some places. And it is also clear that we have some porosities. They are identified here by the red arrows. We tried to account for the porosity level by using ImageJ software, and according to our calculations, the value was lower than 1%. So it's good in this kind of manufacturing process, in our opinion. So regarding the hardness profiles, so we can see here the measurements in different directions, longitudinal and transverse direction, evaluated into orthogonal lines. If we analyze the variations over the distance, and if we compare the average values, we can see that these values are basically the same, regardless of the direction and the plane evaluated, which is also good in our perspective regarding the reproducibility of the manufacturing process. So now let me show you some results about the cyclic response. So here we can compare two full tests when conducted under constant amplitude loading and when conducted under variable amplitude loading, both for a maximum strain amplitude of 1%. And if we compare the response over time, we can see in both cases that the material exhibits a softening behavior. So the stresses, the maximum stress reduces over time. And it is also clear that this response is stronger for the variable amplitude loading. I think is not surprising, because we are changing the loading level during each cycle, which forces the material to a strong response in order towards the equilibrium. And here we can also see the midlife cycles identified by the red lines. And I would like to show you more or less the same information, but in a different way. In this case, at the top, we have a test conducted under constant amplitude loading, and the other two were conducted for different levels of variable amplitude loading, and we see more or less the same situation. So we can identify a small variation cycle by cycle, and in this case, it is more evident for variable amplitude loading that the response changes more significantly when the material is subjected to this kind of loading. So, but if we analyze the full picture, we can see that we have a stabilized behavior. Here is the middle of the test, the midlife cycle. And we tried to predict the fatigue lifetime only using the midlife cycle. So I would like to show you two examples under variable amplitude loading regarding the midlife cycles. So here we can see an interesting effect. So in fact, we have found a mean stress effect. If we compare the maximum and minimum values, we can see that they are not similar. The cycles are not symmetrical. So we would like to include these values in our fatigue life prediction model. So regarding the prediction model, we tested two simple methods, the Baskin, Coffey, Manson, and the Smith, Watson, and Topper. Here you can see the fitted functions for Baskin, Coffey, Manson model based on constant amplitude loading tests. And here is summarized more or less the process adopted to estimate fatigue lifetime. So we combined the midlife cycles selected as I explained before, together with the Minor's law. So basically we calculate the values associated to these two parameters, these two models for each midlife cycle, and then we sum the damage, and based on these calculations we can estimate the fatigue lifetime. So here we compare the experimental life and the predicted life using both approaches. As you can see here, the Baskin, Coffey, Manson led to better results. They are balanced and are close to an average error, close to zero. And this is good in terms of fatigue life prediction. Regarding the Baskin, Coffey, Manson, so we can see that the average error is shifted to the unsafe side, which is not positive. So to conclude my presentation, I only would like to show you a few images about the fracture surfaces and the failure mechanisms. At the top, some images collected at constant amplitude loading, and at the bottom under variable amplitude loading. But if we compare the fracture surfaces, we can see that the failure mechanisms are basically the same. So we have found in some cases multi-crack initiation phenomena. So we can see several cracks located near the surface or close to the surface, and then they propagated towards the center of the specimen, and here is basically the same. So we have found a brittle dominant failure mechanism, but some evidences of ductile failure, and as expected, some typical defects associated to the printing process. So lack of fusion defects and molten particles, and so on. So only a few conclusions. So regarding the microstructure, we have found that the microstructure was rather coherent and formed by martensitic needles. Hardness profiles were similar, regardless of the direction analyzed. We have found a typical softening behavior, irrespective of the strain amplitude of the loading type, and we can conclude that the SWT model, along with Minor's law, is able to estimate the fatigue lifetime under variable amplitude loading. So regarding the failure mechanisms, we have found multi-crack initiation phenomena, and the failure was initiated from cracks located at the surface of the specimens. So thank you.
So thank you very much. Some questions?
Any treatment or other treatment after processing?
In this specific research, no, but we are doing more tests with HIP treatment. In the future, I will have some results about the effect of HIP treatment in this material. But I know maybe you have some good suggestions to improve the cyclic behavior.
Thank you.
Thank you.
Okay, some other questions? Okay, if not, then we can go to the next. I think you are again. Okay, hello again. Yes, Then you can start with the topic comparison of different averaging methods and damage loss in multi-axial fatigue life assessment of notched components.
So in this second talk, I'm going to talk about the possibility of using simple linear elastic approaches combined with notch plasticity correction to estimate the durability of notched components under multi-axial loading. Yes, so this is the outline, motivation, the model that we will use to perform this type of comparison, experimental and numerical procedures, some results, and a few conclusions. So multi-axial fatigue is a very complex problem, and when we combine it with severe geometric discontinuities, the problem is even more challenging. Regarding the fatigue life prediction models, in general, they are organized into three groups: stress-based, strain-based, and energy-based approaches. And the notch effect is generally accounted for by using the theory of critical distances, the strain energy density, or fracture mechanics concepts. However, most of these models require a huge number of material constants and require sophisticated numerical simulations, which makes the process time-consuming. In some cases, this approach is not completely suitable for daily problems. So the idea is, can we estimate the fatigue lifetime under multi-axial loading using simple methodologies? So I'm going to answer this question. So our idea is to explore, the possibility of using simple linear elastic models combined with notch plasticity correction. So the proposed methodology is summarized here. So we rely on the idea that the multi-axial stress state can be reduced into an equivalent uniaxial stress state. So in this way, we basically need to compute a relationship between the fatigue damage and the number of cycles to failure. So we can do that using a simple one parameter damage loss, for example, written in terms of stresses, strains, or energy quantities. We perform a number of tests under fully reversed conditions, and we evaluate the main variables, and we define this kind of function. So in my talk today, we are going to use three different approaches, simple ones: the Baskin-Coffey-Manson, the total strain energy density, and Smith, Watson, and Topper. And in a second stage, when we are dealing with the multi-axial loading conditions, basically we perform it numerically using a linear elastic approach, and then we calculate the effective value near the notch processed zone. So in my case, I'm going to calculate the effective value by using the theory of critical distances, more specifically the line method. Basically, I need to compute the material characteristic length by performing high cycle fatigue tests and fatigue macro tests. And then we define the fatigue process zone, and by applying the line method, we calculate the effective value. And then by using notch plasticity techniques, today I'm going to use these three approaches: Neuber's rule, Glinke's rule, and the modified Glinke's rule. So basically we generate an equivalent stress strain loop, and then we calculate the properties regarding these three models, and we estimate the fatigue lifetime. So in order to test this idea, basically we perform first some low cycle fatigue tests. Here you can see the geometry and the tested strain amplitudes. So the selected material was a high strain steel, 34 chromium nickel molybdenum 6, and here you can see some mechanical properties. In a second stage, we performed a number of multi-axial fatigue tests under proportional bending torsion. So we considered a solid cylindrical geometry with a U-shaped notch, and we tested it considering 7 different loading scenarios. 3 relations between the bending and torsion moment, 2, 1, and 2/3, and 3 orientations of the bending moment with respect to the node root, 0 degrees, 45 degrees, and 90 degrees. So the tests were conducted under pulsating loading conditions, and for each case we considered at least 3 different stress levels. So in order to evaluate the stresses and strains at the node root, we created 2 numerical models. Here you can see the mesh. It is very refined near the node region, and basically the difference is that in the first model we used a simple linear elastic approach. That is the core of my talk, and for comparison purposes we created a Armstrong-Frederick-like model that is able to account for isotropic hardening and kinematic hardening, and here are the fitted constants. So now let me show you first some results about the low cycle fatigue campaign. So here we can see 3 tests conducted at 3 different strain amplitudes, and here you can see the fatigue lifetime for each one of them. And the gray color represents the full test, while the other 2 cycles represent specific moments of the test. The black one represents the second cycle, and the red one represents the midlife cycle. So in this case, once again, we can see a clear softening behavior. It is even more clear in this figure that represents the variation of stress amplitude over the number of cycles. And in fact, we can see a typical softening behavior, then a saturated like stage, and in the final stage, a rapid decrease in the stress amplitude. And once again, we selected the midlife cycle as representative of this loading level. So now we are able to create the 1 parameter damage loss. So here I'm showing you 3 stable loops, but we considered all tested cases, and then we can fit the points using this simple approach. And as you can see here, we are able to do that with a high correlation. But we can do the same using, for example, energy quantities. So in this case, we can account for the plastic strain energy represented by the red lines, and the elastic positive energy represented by the gray triangles. And as you can see here, we can also fit all this information in a very simple way, only with 3 constants, and the correlation is relatively high. And finally, regarding the SWT parameter, we can do the same. So we can account for the area represented in gray for each test, and we can plot it against the number of cycles, and we can fit the data once again with high correlation. So in conclusion, regarding the 1 parameter damage loss, we have now 3 equivalent methodologies to fit the data, but the question is, how do they behave under multi-axial loading? Can we assume that they will behave in the same way? So I would like to answer this last question. So here are our predictions in terms of multi-axial loading. So in this first slide, we compare the 3 methodologies using Neuber's correction. So as you can see here, the models behave differently. In this case, the results are very good, in our opinion. In the other cases, we cannot say the same. So energy is very good, but the other 2 approaches led to conservative values. In our opinion, this is a little bit excessive, and you can see here a comparison in terms of probability density functions. In fact, the model based on the energy leads to errors quite close to 0, and the standard deviation is small. In the other cases, as expected, they are shift to the conservative side, and the scatter is much higher. So now regarding the linkage approach. So overall, it seems that the behavior is more or less the same, but if we compare the previous results represented here by the dashed lines with those obtained by Glinka's approach, we can see that it is a little bit more accurate. The average error is close to 0 and the standard deviation decreased a little bit, which is good. And finally, regarding the modified Glinka's approach, I would like to show you maybe the comparison. We can see that there are no relevant differences, but if we analyze it closely, we can conclude that it is a little bit better than the original Glinka's model. So finally, to conclude my results section, I would like to compare predictions based on the linear elastic approach and the elastic plastic, but only for the energy model due to time limitations. So as you can see here, the differences are not relevant. So in part, it demonstrates that it is possible to estimate the fatigue lifetime under multi-axial loading using simple linear elastic approaches. And here we can see that, in fact, the elastic plastic approach is more balanced. The average error is almost 0, but surprisingly, the scatter is a little bit higher than the one obtained by our linear elastic approach. So to conclude my presentation, only 4 short conclusions. So basically, we can conclude that the linear elastic models combined with notch plasticity correction rules are able to estimate the fatigue lifetime under proportional bending torsion. In fact, the energy-based approach led to correlations with all points within scatter bands with factors of 2. Regarding the notch plasticity correction rules, Glinka's and modified Glinka's were the best ones. And comparing both elastic and elastic plastic predictions, we concluded that they are comparable, so which is good in our perspective. Thank you very much.
So thank you. Any questions? I have a question. For which material did you do? Was this also additive manufactured or a conventional one?
Yes, we tested these approaches in different types of materials. Today, I only presented for conventional materials, but we tested the methodology also for maraging steel, and the conclusions were basically the same.
Okay.
Thank you.
So, other questions?
So, Professor, thank you for your very interesting presentation. The subject is very difficult, and you presented it very well. And my question is, from your experience, do you think that those methods, those approaches, can we justify that it would be also validate for other materials such as composites? Does the approach will work or not very well?
Honestly, I think these methods are not a good solution for composite materials because the behavior is much more complex. I tested successfully the energy approach for composites to estimate the fatigue lifetime, but only under uniaxial loading conditions. Under multi-axial, probably it will be possible, but it will not be easy to create a methodology to assess and to reduce the multi-axial stress state into a equivalent uniaxial one. I think it will be complex, but we can try.
Yeah.
Thank you.
Maybe if I can just a small comment. Well, it all depends on the core. I mean, the predictor of fatigue damage. In this case, if we look on the Smith-Watson-Topper or the others formulas, there are still tables for homogeneous materials like steels. But of course, if we can propose, of course, much more complicated damage predictor from composite materials, I know, short fiber or long fiber. I know why you ask, because you have similar problems in composite materials. The global framework of this is much more efficient than other one if we use it for your materials, composite materials. But the core, so predictor, should be different. In this case, we used well known and a little bit modified, but for the composite materials, we need to elaborate or modify existing criteria, but not for the homogeneous materials, but for non-homogeneous materials. And then more or less it should work. Thank you.
Thank you again. And we will come to the next.
The next presentation will be once again virtual. I have to rearrange the screen. Pani Patrycjo. Jakieś problemy. Pani Patrycja, czy pani mnie słyszy? She is present, but...
O, halo, słychać mnie może?
Słychać.
O, dzień dobry bardzo.
Pozwolę sobie zapowiedzieć. Patrycja Lau, Piotr Paczos, analiza wytrzymałości zmęczeniowej osi kolejowej. Patrycja, czy pani mnie słyszy?
Tak. To,
She is present, but...
halo? O, halo, słychać mnie może? O. Halo?
Słychać.
Dobrze.
Może pani udostępnić ekran.
O, dzień dobry jeszcze raz. Czy wszystko dobrze widać?
Tak.
Dobrze, to szanowni państwo, chciałabym dzisiaj zaprezentować właśnie analizę wytrzymałości zmęczeniowej osi kolejowej. Tutaj krótki plan prezentacji. Zacznę od wprowadzenia, opiszę badaną oś, przedstawię obliczenia analityczne, numeryczne oraz doświadczalne i podsumowanie. Chciałabym właśnie zauważyć, że pomimo nieustannie i dynamicznego rozwoju transportu zarówno samochodowego, jak i lotniczego, to jednak transport kolejowy wciąż jest tym istotnym środkiem transportu towaru, a także osób. Wynika to pewnie głównie z wciąż rosnących cen paliwa oraz nieustannie zakorkowanych ulic wielu miast. Jeden z najważniejszych zespołów pojazdów szynowych jest zestaw kołowy. Jest to układ funkcjonalny właśnie pojazdu szynowego, który składa się z osi oraz z dwóch tłoczonych kół, które są przystosowane właśnie do toczenia po szynach. Konstrukcja zestawu kołowego jest niezwykle istotna i ważna z technicznego punktu widzenia, ponieważ właśnie to od niego zależy bezpieczna jazda, a także bezpieczeństwo osób, które poruszają się tym pojazdem. Tutaj w swojej pracy skupiałam się właśnie na osiach tocznych, towarowych typu A, i żeby właśnie podkreślić też i zaznaczyć istotę badań osi, a także jak ważną właśnie rolę pełnią one w konstrukcji całego pojazdu szynowego, chciałabym przytoczyć tutaj pewną historię, a mianowicie w 2009 roku we włoskim miasteczku Viareggio, mam nadzieję, że dobrze wymówiłam tę nazwę, miała miejsce katastrofa kolejowa. I pociąg właśnie wiozący cysterny z gazami LPG wykoleił się na skutek właśnie pęknięcia pierwszej osi pierwszego wagonu, a to spowodowało wybuch gazu, który spowodował zniszczenie budynków mieszkalnych położonych właśnie blisko tej katastrofy. I tutaj przyczyna właśnie mogła być nawet najmniejsza ryska, która gdzieś tam na przykład od tłucznia była. Ktoś źle sprawdził, ponieważ przy eksploatacji takich wagonów bardzo ważne jest właśnie oglądanie tych zestawów kołowych, czy czasem nie ma żadnych uszkodzeń i gdzieś czasem ta propagancja pęknięcia doprowadziła właśnie do tak tragicznego w skutkach zdarzenia. Tutaj właśnie w swojej pracy będzie przebadana, w mojej pracy przebadałam oś toczną, właśnie typu A i tutaj właśnie te osie toczne właśnie są najbardziej narażone na te zużycie zmęczeniowe i właśnie ze względu na dużą odpowiedzialność osi w konstrukcji całego tak naprawdę pojazdu do wykonywania takich osi stosuje się zazwyczaj właśnie znormalizowane materiały oraz odpowiednio też obrobione mechanicznie oraz cieplnie. Obliczenia analityczne natomiast wykonuje się ze względu na podstawie normy europejskiej PN 13103 i standardowo wykonuje się właśnie obliczenia rozważając przekroje najbardziej narażone. Jednak tutaj właśnie w pracy przebadałam tylko 2 przekroje, w których były naklejone właśnie tensometry podczas badania stanowiskowego, tak aby móc porównać te wyniki. Tutaj właśnie przedstawiłam, oczywiście obliczenia są wykonane zgodnie z normą i tutaj 3 od dołu ostatnie są wyniki właśnie tych 2 tensometrów. Następnie w celach właśnie porównawczych również przeprowadziłam badania numeryczne i ocena wytrzymałości właśnie została wykonana na modelu obliczeniowym ukazanym tutaj na rysunku. Wymiary geometryczne oraz kształty zostały właśnie przyjęte na podstawie rysunków, a warunki brzegowe zostały zamodelowane tak, żeby odpowiadały tym, które są na badaniu doświadczalnym były, które zostaną także zaprezentowane na późniejszych slajdach. Tutaj są wyniki właśnie w miejscach umiejscowienia tensometrów podczas próby stanowiskowej. I tutaj badania właśnie stanowiskowe zostały wykonane w sieci badawczej Łukasiewicz w Poznańskim Instytucie Technologicznym, właśnie na stanowisku przeznaczonym do takich badań wytrzymałościowych osi zestawów kołowych. I co ciekawe, jest to krajowe, oryginalne rozwiązanie i ta maszyna została wykonana w zakładzie cegielskim właśnie w Poznaniu na podstawie dokumentacji tutaj właśnie z Łukasiewicza PIT. Jednak to było już jakiś czas temu i wtedy to nie był jeszcze Łukasiewicz, ale to był ośrodek badawczo-rozwojowy pojazdów szynowych. I takie badania obejmują właśnie wykonanie próby zmęczeniowej w zakresie 10 milionów cykli oraz oczywiście kontrola tensometryczna. I polega właśnie do takiego badania dostarczona jest próbka osi normalnych rozmiarów w formie takiego półzestawu, czyli oś oraz jedno wtłoczone koło. Zamocowana jest tutaj do maszyny i tutaj są 2 pulsatory, które bezpośrednio obciążają właśnie próbkę na jej końcach oraz także 2 pulsatory, które służą do dynamicznego wyważenia sił, które działają na fundament maszyny. I chciałabym tutaj właśnie też pokazać, jak działa taka maszyna. O i tutaj jeszcze... Tutaj są właśnie wyniki z wszystkich 3 prób. Co ciekawe, właśnie wszystkie 3 próby pokryły się, mimo że na przykład norma nie przewiduje tutaj badań numerycznych, to jednak wykorzystanie tej metody okazuje się również trafne, szczególnie tutaj jeżeli chcemy dokonywać jakiejś modyfikacji osi, gdzie tutaj przy tych badaniach symulacyjnych rzeczywiście może być troszkę prostsze wprowadzenie różnych modyfikacji i sprawdzenie właśnie, jak dana modyfikacja wpłynie na rozkład w całej osi. Żadna tutaj nie przekroczyła naprężeń dopuszczalnych, jednak co ciekawe, tutaj są tylko 2 tensometry, dlatego też to była oś kontrolna podczas badania koła, jednak tu zadziała się bardzo pod sam koniec praktycznie próby. Nastąpiła bardzo ciekawa rzecz, a mianowicie nastąpił przełom. Tutaj było właśnie pokazane, jak już przełamana oś pracuje. Oczywiście tutaj zadziałały czujniki bezpieczeństwa, wyłączyła się maszyna, ale byliśmy właśnie ciekawi, ponieważ nie była oś, to była po prostu taka oś testowa, nie do użytku, nie dostarczona przez klienta, to właśnie tutaj pozwoliliśmy na propagandę tego pęknięcia, żeby zobaczyć może też, co było istotą tego. Tak wyglądał tutaj przełom zmęczeniowy tej osi. Można powiedzieć, że taki akademicki przykład, bo bardzo ładnie tutaj widać właśnie linię zmęczenia, strefę zresztą zmęczeniową i resztkową oraz takie 2 ogniska. Jeżeli się przyjrzymy tym ogniskom z boku, w jednej części oraz w drugiej osi, można zauważyć, że te części są takie wypukłe, więc można się właśnie zastanawiać, skąd tutaj powstał i najprawdopodobniej to pęknięcie nastąpiło w wyniku niejednorodności kryształu właśnie osi, więc możliwe, że gdzieś tutaj przy kłuciu po prostu ten kryształ nie został odpowiednio jakby zmielony, rozmiażdżony do takich odpowiedniego jakby rozmiaru kryształu. I co ciekawe, właśnie mimo, że istnieje też norma, która zakłada jakby różne, bardzo wszelakie tutaj sprawdzanie osi i materiału pod czerwień, to tak naprawdę tutaj ta niejednorodność kryształu jest bardzo trudna do wykrycia, praktycznie no niewykrywalna, więc też fajnie takie jednak badania wyrywkowe paru na przykład tych osi z serii przeprowadzać na badanie na maszynie zmęczeniowej, ponieważ właśnie można wykryć jakieś takie trudno wykrywalne w innych badaniach wady osi. I właśnie tutaj podsumowanie, że metoda numeryczna, mimo że norma nie przewiduje tutaj badań symulacyjnych, także sprawdza się i dobrze obrazuje rozkład naprężeń w danym modelu, co widać właśnie na podstawie tego, że wyniki ze wszystkich 3 badań pokryły się. Ponieważ oś jest bardzo istotna w całym pojeździe i wpływa na bezpieczeństwo jazdy, bardzo istotne jest, aby odpowiednio dobrać materiał, zaprojektować i zakonstruować taką oś, a także podczas eksploatacji, że ważne jest bardzo doglądanie tej osi, czy na pewno nic nie jest uszkodzone, ponieważ no jeżeli ta warstwa, ta powłoka ochronna gdzieś tam zostanie uszkodzona, to sama oś bez tej powłoki jest bardzo narażona właśnie na różne właśnie pęknięcia poprzez nawet właśnie odprysk tego tłucznia. I istotne jest całkiem właśnie, żeby zbadać parę takich osi z serii wyrywkowo na tutaj maszynie zmęczeniowej, gdyż właśnie można dostrzec takie wady, które no niestety za pomocą innych metod nie jesteśmy w stanie dostrzec. Dziękuję bardzo za uwagę i zapraszam do zadawania pytań.
Dziękuję bardzo za prezentację. Czy są jakieś pytania?
Dziękuję bardzo za prezentację. Ja mam pytanie, bo użyła Pani słowo kryształ. Chodzi o niejednorodność mikrostruktury, ziaren.
Ziaren, tak.
Chodzi o jednorodność struktury ziaren, tak? A były wykonane również zgłady metalograficzne tych powierzchni, które by to potwierdzały?
Nie, właśnie dlatego mówiłam, że prawdopodobnie potem po prostu tutaj właśnie po konsultacji takiej bardziej doświadczonej, ponieważ to nie była oś jakby ani klienta, to też jakby nie mieliśmy środków na takie dokładne badania tego, bo to po prostu była taka oś kontrolna użyta po prostu tylko do badania koła, więc takie szczegółowe niestety nie były badania, tylko właśnie po tym przełomie najprawdopodobniej to mogło być właśnie przyczyną.
Dobrze, dziękuję bardzo.
Jeszcze jakieś pytania?
Dziękuję. Dziękuję za bardzo ciekawą prezentację. Temat jest aktualny i ważny. Ja mam takie pytanie, jeśli można. Czy analizowaliście Państwo w trakcie swoich rozważań wymuszenia, jakie w warunkach rzeczywistych działają na te osie, czyli zakres częstotliwości, amplitudy oraz 2, jakie obciążenia były, zakres częstotliwościowy obciążeń, które Państwo stosowali już na maszynie wytrzymałościowej w swoich pracach. Dziękuję.
W sensie jakby osobno, bo tutaj jakby już maszyna ma dostosowane tej siły, w sensie są wyliczane tutaj przez osoby pracujące właśnie w laboratorium i my właśnie te siły, które były użyte jakby konkretnie na maszynie, ona tam, to wynika oczywiście tam z normy, to te właśnie siły tutaj pokazane też przy obliczeniach, tutaj siły P, tutaj są, które były na pulsatorach, to właśnie te użyliśmy tutaj podczas naszych badań zarówno analitycznych, jak i mesowskich.
Zakres częstotliwości, to jest istotne w badaniach zmęczeniowych i one powinny odpowiadać częstotliwościom w warunkach rzeczywistych występujących.
Zapewne tak jest właśnie, no, przez to są tutaj certyfikowane właśnie badania na tej maszynie zmęczeniowej, więc no jakby te obciążenia raczej muszą właśnie być odpowiednie w stosunku do tego, co się dzieje w rzeczywistości.
Rozumiem, dziękuję uprzejmie.
Dziękuję bardzo. Czy jakieś pytania jeszcze? Jeżeli nie, to dziękuję pani bardzo.
Dziękuję bardzo również.
Jeszcze aranżuję. Kolejna, ostatnia przed przerwą kawową prezentacja. Michał Stosik, Mikołaj Karpenko, Paweł Bury i Paulus Skaczkałkas. Właściwości hydrodynamiczne naprawialnych, elastycznych przewodów hydraulicznych podanych zmiennych obciążenia. Modelowanie i eksperyment. Momencik, ja muszę jeszcze. Można prosić?
Mhm. O, tak. Działa. Dzień dobry Państwu, ja nazywam się Paweł Bury i tutaj wspólnie z zespołem przygotowaliśmy taką pracę. No, tytuł już był przedstawiony, ja może tak nawiążę do tego, co przed chwilą pan profesor zadał pytanie, czy były analizowane właśnie wymuszenia na obiekcie rzeczywistym i czy były badane zakresy częstotliwości. To właśnie ta praca, którą tutaj przedstawię, będzie w tym kierunku. Analizowaliśmy właśnie układ, obiekt, który no w celu właśnie określenia sił, wymuszeń i różnych zjawisk, które gdzieś tam mogą się pojawić. Coś się stało. Wysiło się. Okej. O, działa. No więc tutaj na pierwszym slajdzie przedstawiłem, czy krótko wyszczególniłem obciążenia, które działają na przewód hydrauliczny. Tutaj zajęliśmy się akurat przewodem elastycznym, ale ogólnie w układzie hydraulicznym takie obciążenia występują, czyli po pierwsze są to cykliczne obciążenia wynikające ze specyfiki pracy układu napędowego, hydraulicznego układu napędowego, czyli po prostu dane fragmenty układu raz są poddane niskim ciśnieniom, raz wysokim ciśnieniom. Często są to skoki od praktycznie zerowych ciśnień, czyli bardzo niskich ciśnień do ciśnień maksymalnych dopuszczalnych w układzie. Mamy też takie części, takie obwody w układach hydraulicznych. Drugim obciążeniem, czy składową, tak, jest pulsacja ciśnienia wewnątrz przewodów i ta pulsacja ciśnienia może wynikać, czy mieć źródło tutaj po pierwsze w pulsacji pompy. Pompy stosowane w układach hydraulicznych są to pompy wyporowe. Pulsacja wydajności powoduje pulsację ciśnienia, więc oprócz tego ciśnienia średniego, które nam się może zmieniać, mamy cały czas pulsację ciśnienia. To pokażę później na kolejnych slajdach dokładniej. A dodatkowo możemy mieć pulsację ciśnienia wynikającą z oddziaływania drgań na różne elementy hydrauliczne, w szczególności zawory, i to też postaram się troszeczkę tutaj przybliżyć. No i ostatnie tutaj wyszczególnione to drgania mechaniczne, które są przenoszone z ramy, z całej konstrukcji na przewody hydrauliczne. Pulsacja wydajności, czyli to pierwsze źródło tej pulsacji ciśnienia. Pulsacja wydajności w pompach zębatych w zależności od typu pompy kształtuje się tak, jak to jest pokazane na wykresie. Najlepiej by było stosować pompy, które tutaj są podpisane jako 1, czyli pompy śrubowe, ale one nie spełniają podstawowego warunku, czyli nie mają zbyt wysokich ciśnień, więc rzadko je używamy je tylko do układów takich pomocniczych. Natomiast najczęściej stosowane są pompy zębate i pompy wielotłokowe, tutaj 2. No jak Państwo widzą, pompy zębate mają dosyć dużą pulsację, dochodzi gdzieś do około 30%, zazwyczaj jest to około 20% pulsacji wydajności, czyli jak dla przykładu, jak mamy 100 litrów wydajności, 100 litrów na minutę wydajności średniej, no to przy 20% będziemy mieć plus minus 10 litrów taką pulsację z częstotliwością, no często powiedzmy od 100 do 300 Hz, w zależności od tego, ile mamy elementów wyporowych, więc tutaj ten zakres może się zmieniać. Pulsacja wydajności pompy, ogólnie jakbyśmy analitycznie się przyglądali pulsacji wydajności, jest to taki cykliczny przebieg, tutaj jest pokazany wykres czasowy, to w rzeczywistości analitycznie możemy to wyznaczyć jako taki nakładanie na siebie kolejnych parabol, zazwyczaj, w zależności jeszcze od typu pompy. Natomiast często w obliczeniach przyjmujemy model, tak jak tutaj jest pokazany model w MATLABie, jako zbiór sinusów, zbiór po prostu kolejnych harmonicznych, które ten przebieg nam odwzorowują. No i tutaj widać właśnie widmo częstotliwościowe takiej pulsacji. Dalej te drgania mechaniczne, które mamy w układzie, w zależności czy to jest układ mobilny, czy układ typowo przemysłowy, czy jakiś zasilacz stacjonarny, to te wymuszenia mogą być różne. Tutaj są przedstawione badania własne autorów drgań na płycie zasilacza. Jest to zasilacz stacjonarny, więc to są tylko drgania pochodzące, czy w większości drgania pochodzące od pompy hydraulicznej. I właśnie widać tutaj tą częstotliwość drgań podstawową właśnie wynikającą z pulsacji ciśnienia. Gdyby to był układ mobilny, czyli jakaś koparka, jakieś tego typu maszyny, dźwigi, no to wtedy mielibyśmy dodatkowo jeszcze drgania, zazwyczaj od silnika napędowego, który napędza nam układ hydrauliczny, i dodatkowo jeszcze drgania wynikające no, z poruszania się po nierównym gruncie, które też dodatkowo obciążają układ. Teraz te drgania mechaniczne oddziałują na elementy hydrauliczne, w szczególności na zawory. I tutaj są przedstawione badania, gdzie drganiom mechanicznym poddawany jest taki rozdzielacz proporcjonalny. Raz te drgania są w kierunku równoległym, czy zgodnym z kierunkiem ruchu suwaka, a raz te drgania są w kierunku prostopadłym. I tutaj na wykresie można zauważyć, linią niebieską mamy drgania równoległe do suwaka. Widzimy, że te 40 Hz, które tutaj było podane na ten rozdzielacz, powoduje znaczną pulsację ciśnienia. To jest amplituda pulsacji ciśnienia. Natomiast przy drganiach prostopadle do kierunku suwaka tych obciążeń, tej pulsacji ciśnienia w tym zakresie częstotliwości praktycznie nie ma, tak? Nie widzimy tego. Poniżej przedstawiony jest wykres przemieszczenia, widmo przemieszczenia suwaka tego rozdzielacza. No i właśnie widać, jak w tym zakresie, właśnie w zakresie tych 40 Hz zaczął się wzbudzać, zaczął drgać ten suwak, powodując właśnie tą pulsację ciśnienia. Dodatkowo były też robione badania wpływu drgań na zawory, na mikrozawory w mikroukładach hydraulicznych. Tutaj jest schemat takiego stanowiska, właściwie zawór maksymalny, mikrozawór maksymalny został ułożony na wzbudniku elektromagnetycznym i sprawdzaliśmy tutaj, jak te drgania zewnętrzne wpływają na właśnie pulsację ciśnienia w układzie. Na rysunkach po pierwsze widzimy widmo pulsacji ciśnienia bez drgań mechanicznych, czyli to jest tylko pulsacja wynikająca z pracy pompy. Do tego dokładamy drgania mechaniczne, drgania w sensie drgania tego zaworu, mikrozaworu, i widzimy, że w tym zakresie częstotliwości pojawia nam się znaczny wzrost amplitudy pulsacji ciśnienia, no, który finalnie obciąża nam te przewody. Tutaj jest taki krótki filmik pokazany, jak też wpływają drgania mechaniczne na przewody, jeśli w jednej z podpór będziemy wymuszać drgania. Tak, przewody elastyczne zaczynają wtedy drgać. No, w zależności od częstotliwości będą mieć różne postaci drgań, to akurat mamy pierwszą składową. No i te drgania mogą powodować różne uszkodzenia. Drgania takie mechaniczne mogą powodować takie uszkodzenia w postaci przetarć płaszcza zewnętrznego. Ogólnie budowa przewodu hydraulicznego jest tutaj pokazana tak w skrócie na tym schemacie. Mamy warstwę wewnętrzną, zazwyczaj z jakiegoś elastomeru, który odpowiada za szczelność tego przewodu, żeby czynnik nie wydostawał się na zewnątrz. Później mamy jedną bądź kilka warstw wzmacniających oplot i ten oplot może być z drutów stalowych, może to być oplot z różnych tworzyw sztucznych, bo to mogą być nylonowe, lniane, mogą być też kewlarowe, też takie przewody mamy. I na zewnątrz mamy kolejną warstwę z elastomeru. Zazwyczaj jest to elastomer o podwyższonej odporności na ścieranie, po to, żeby też zabezpieczyć te warstwy właśnie wzmocnienia, ten oplot przed przetarciem. No i też ma ten oplot, ta warstwa zewnętrzna ma zapewnić szczelność, żeby środowisko korozyjne nie dostało się do środka tego przewodu. I jak widać też na tym rysunku tutaj, ta warstwa zewnętrzna została uszkodzona, korozja już tam postępuje, tak? Już mamy taki rudy kolor, więc widać, że ta siatka stalowa koroduje, więc to jest już początek degradacji tego oplotu. No i finalnie skutkuje to takim pęknięciem, jak tutaj jest pod spodem, czyli ten oplot pęka, no i czynnik wydostaje nam się na zewnątrz, zazwyczaj to wygląda w ten sposób. Oczywiście, jeśli to uszkodzenie jest gdzieś tam poza obszarem zamocowań, bo dochodzi też nam czasami tutaj do uszkodzeń, właśnie dosyć często do uszkodzeń w tym obszarze, ale to na koniec troszeczkę bardziej przybliżę. Jeżeli powstanie takie uszkodzenie, jak pokazałem wcześniej, czyli na środku gdzieś tego przewodu, czy w okolicach takich, gdzie da się wstawić taką złączkę naprawczą, jak tutaj widzimy już po naprawie, czyli mamy uszkodzony fragment, przyjeżdża serwis mobilny, zazwyczaj to tak wygląda, że przy takich maszynach ciężkich przyjeżdża serwis mobilny, zakłada tam taką złączkę, maszyna może pracować dalej bez straty czasu, tak, bez dużej straty czasu. Taka złączka no, wprowadza dodatkowo, w sensie zmienia sztywność tego przewodu, dodatkową masę, tak, jest to zmiana obiektu, jakby na to nie patrzeć. Do tych modelowań, które tutaj były prowadzone, przyjęliśmy takie parametry, czyli warstwa wewnętrzna jest to guma NBR, zbrojenie siatka z drutów stalowych, natomiast warstwa zewnętrzna to jest NBR plus PVC, czy tam no, jest taka kombinacja właśnie, żeby była trudnościeralna i złączka, akurat tutaj w tym przypadku było przyjęte, że jest to złączka ze stali nierdzewnej, natomiast nie zawsze to są złączki ze stali nierdzewnej, to zależy od środowiska, w jakim układ pracuje. Jako pierwsze zostało przeprowadzone modelowanie przepływu przez taki naprawiany przewód no, w oprogramowaniu ANSYS Fluent. No i już przechodząc od razu do wyników, żeby tutaj nie zanudzać warunkami brzegowymi, widać tutaj, jaki jest spadek ciśnienia. Przy przewodzie nienaprawianym, czyli u góry mamy przewód nienaprawiany, rozkład ciśnienia jest w miarę proporcjonalny na długości, oczywiście w środku, tak, bo pomijając tam inne zjawiska, w miarę proporcjonalny na długości tego przewodu. Natomiast przy przewodzie naprawianym widzimy, że tutaj przed przewodem jest w miarę stałe ciśnienie, tutaj dochodzi do znacznego spadku ciśnienia i znowu mniejszy ten spadek. Finalnie, jak sobie popatrzymy na skalę, różnica, najlepiej było porównać tutaj te fragmenty, taka złączka wprowadza nam spadek ciśnienia, który ogólnie wpływa na obniżenie sprawności układu, czyli nie jest to do końca dobre. Jeżeli wprowadzimy wiele takich złączek, to będzie problem. OK. W takim razie tutaj przyspieszę troszeczkę. Rozkład prędkości już pominę w takim razie i badania dynamiczne, które robiliśmy, czyli badania drgań takiego przewodu, skonstruowaliśmy stanowisko, w którym mierzyliśmy siły, jakie działają, jakimi przewód oddziałuje na podpory. Mieliśmy podporę zasilającą, w każdej i podporę spływową, tak, czyli linię powrotną. W każdym z tych podpór były czujniki ciśnienia, pulsacji ciśnienia, czy ciśnienia statycznego, pulsacji ciśnienia i temperatury oraz pomiar sił. Siły były mierzone tylko w osiach przewodu. Natomiast tutaj ten fragment układu odpowiadał za wprowadzanie odpowiedniego napięcia, żeby ten przewód miał lekkie napięcie. Zawsze tak jest, że ten przewód jest zamocowany i to napięcie jakieś tam występuje. Układ hydrauliczny może pominę, tylko powiem tylko tyle, że zasilany był pompą wielotłokową o zmiennej wydajności, więc mieliśmy możliwość też zmiany wydajności przy zachowaniu stałej częstotliwości wymuszenia. I tutaj są wyniki prędkości drgań tego przewodu, to był pomiar na środku wibrometrem laserowym. Proszę zobaczyć, że dla różnych parametrów, dla wszystkich ciśnienie było statycznie takie samo, natomiast u góry widzimy zmienia się natężenie przepływu, a tak w poziomo zmienia nam się obciążenie, naciąg, czyli tu mamy 10 kg, tutaj 5 kg. Dla każdego z tych przypadków, w szczególności dla pierwszej składowej, która zazwyczaj jest dominująca, widzimy, że przewód naprawiany ma mniejszą amplitudę drgania. Czyli wydawałoby się, że to jest w sumie nawet dobrze, tak? Bo ta amplituda jest mniejsza. Jednak jak patrzymy na amplitudę siły, która ten przewód oddziałuje na podpory, widzimy, że tutaj niestety przewód naprawiany, czyli ten, który ma większą masę na środku, zwiększoną sztywność też tam w tym miejscu, powoduje wzrost siły, amplitudy siły działającej na te zamocowania. Największym problemem jest to, że jeżeli mamy przewody mocowane czy w taki sposób, czy tutaj bezpośrednio do przewodów stalowych, na końcach zazwyczaj są złączki albo spawane, łączone, jest złączka spawana do rury, albo mamy pierścienie zaciskowe. Zwiększone siły działające na takie złącze może powodować właśnie pękanie tych połączeń spawanych, może powodować wyruszanie się też tego złącza zaciskowego, a bardzo często zwiększone siły mogą spowodować też wyrwanie takiego przewodu z okucia, czyli kolejną awarię, czyli niestety może nam to przyspieszyć awarię. No i przechodząc już do podsumowania, tutaj te przewody hydrauliczne właśnie są poddane licznym wymuszeniom, w szczególności tym o charakterze okresowym. Złącze takie naprawcze zmniejsza nam sprawność układu poprzez zwiększony spadek ciśnienia i pomimo tego, że ta amplituda drgań spada właśnie ze względu na większą sztywność, masę, niestety siły na końcach, czyli siły w tych zamocowaniach wzrastają, co może właśnie zwiększać ryzyko kolejnych uszkodzeń. I to na tym chciałbym zakończyć.
Dziękuję bardzo. Czy są jakieś pytania do prelegenta?
Ja mam tylko pytanie właśnie, jeżeli ta sprawność spada, to czy wiemy, o ile ta sprawność spada i dlaczego w takim razie nie zastosujemy mimo wszystko wymienienia całego przewodu, a stosujemy zestawy naprawcze?
To wynika, wyliczyć nie ma problemu, bo jesteśmy w stanie określić, jaki jest spadek ciśnienia i jesteśmy w stanie określić, jaki to jest dla konkretnego układu, jaka to jest strata. Ciężko powiedzieć, do tego przypadku też by można było to określić, tak, bo tam znamy tą różnicę ciśnienia, ale to by trzeba było analizować każdy układ osobno. Natomiast jeśli chodzi o stosowanie tych złączek, to jest kwestia pieniędzy, bo jeżeli maszyna się psuje, dzwonimy po serwis mobilny, który przyjeżdża i oni szybko naprawiają nam taki przewód. Nie zawsze taki serwis ma dostępne wszystkie złącza, bo jakby chciał zrobić nowy przewód, to musi mieć te złącza nowe, musi mieć odpowiedni przewód, więc to może wymagać dłuższego czasu realizacji. No wiadomo, przestój maszyny to też się wiąże z ogromnymi stratami zazwyczaj. Dlatego raczej lepiej by było te przewody szybko naprawić, ale w najbliższym czasie ten przewód wymienić. Tak to powinno być zalecenie. Tak?
A ta sprawność to ma tak o 5% spadać?
Nie, mniej, raczej mniej.
Właśnie, to są takie małe liczby.
Tak, ale finalnie jak więcej sobie takich napraw zrobimy, to może się okazać, że tego będzie więcej. Tak?
Dziękuję bardzo za prezentację.
Dziękuję bardzo.
Dziękuję bardzo. Kolejne pytania jakieś? Jeżeli nie, to dziękuję bardzo. We are ending this session. It's time for a coffee break. And we have to start with plenary session, plenary lecture from China. Do you have to?
Yeah, it's 15-minute coffee break. I would like to invite you to the neighboring room, and we will meet together again at 11:20. So.
Zadać tak pytanie. Chciałem miałem okazję na studiach jeszcze też pracować przy naprawianiu koparek. Mechaniki naprawialiśmy, nie wiem, czy kojarzycie pan. Chyba najwięcej we Wrocławiu tych koparek jest. Ale tak już odnośnie tych przewodów samych, nie? Bo mówił pan, że go napięliście wstępnie, a badaliście to przy jednym poziomie napięcia, no bo
Różne
no
poziomy.
właśnie, nie? No bo po prostu nie wydarzy,
Nie,
napniemy, bo będzie inaczej odpowiadać.
1, 5, 10 kg żeśmy dokładnie różni.
No i właśnie nie wpływało to na odpowiedź układu.
Ale tendencja jest zawsze taka, że jeżeli mamy właśnie to złącze naprawcze, to praktycznie każde wyniki, które przerobiliśmy, zawsze to